Okay, so hi everyone. I will talk to you about some of the recent results that we got on deep learning inference using phase change memory. So this is work that we've been doing for quite some time now at IBM. I will briefly introduce, give a short introduction to deep learning with in-memory computing first. Then after that, I will describe how we can do this with phase change memory technology. And then I will focus most of the presentation on the latest experimental results that we got on the new chip that we got back. So this is this IBM Hermes project chip. And then finally, I will also present a little bit of the hardware acceleration kit that we have in order to simulate deep learning inference and training also with in-memory computing. So just as a short introduction, I mean, it has been also already introduced, but so the idea of in-memory computing is basically to kind of try to eliminate this bottleneck, right, that we have in conventional processing and memory unit, where we essentially, transfer data back and forth all the time between the processor and the memory here, right? So, and here what we could think of, I mean, if we want to, get rid of this bottleneck, is essentially to do the computation directly in the memory in some so-called, computational memory that would be sitting here, right? And then just by sending an instruction with the processor, then we can execute this function f, directly in the memory using the analog properties of the memory devices. So as Onur rightly pointed out at the beginning and morning, we cannot hope to do like a general purpose computing with this kind of scheme, because simply, the operations that you can do here are essentially tied to the analog properties of these memory devices. So you can just do certain computational tasks, not everything with this. So it's very unlikely that this will become general purpose, but on the other hand, you can explore certain tasks with this computational memory. So it has been already shown that you can do some logic operations in DRAM, for example. And what I will describe mostly are the arithmetic operations, and that is mainly matrix vector multiplications, which is essentially the bulk of the computations we do for deep learning inference. And as I said, how we do this is by exploiting the physical attributes and the state dynamics of the memory devices. So what we use at IBM, I mean, there are different memory technologies we can use for doing processing in memory. So essentially all memory technologies can be used to some extent, but here what we use here is phase change memory. So phase change memory, what it is, it's essentially, it looks like this. So it's a memory, it's a phase change material. So this is the material here, it's just sandwiched between two electrodes that are usually not the same dimension, as you can see here. So if we want to program this memory, we essentially send a high current pulse that will amorphize this material and make it more resistive. So that will create a high resistance state here, which is usually called like the reset state. So this could correspond, for example, to logic 0. And then if we want to bring it back to the low resistance state, then we will apply a lower amplitude pulse that will essentially crystallize this amorphous region here and make it more conductive. And then we end up with a fully crystalline material in here that has a lower resistance. So this is how we write phase change memory, and how we read it is by simply, applying a low voltage pulse, and we read the low resistance. So in this state, it will be a low resistance. So that means potentially logic 1, and here high resistance logic 0, for example. And we've looked at a lot of different applications in this review paper that people have looked at for by using computational memory with resistive memory devices. So that is the kind of class of memory devices that phase change memory belongs to. So yeah, these are a very wide range of applications, spanning from like generating random numbers that use basically the stochastic properties of the devices, up to like scientific computing, where you can solve linear equations and do tasks that require very high precision. And then in the middle we have kind of the what people have been mostly looking into, which are the signal processing and machine learning applications. And in that is also deep learning. where you know, the focus of this presentation will be on deep learning inference here. So. And yeah, so why deep learning inference is interesting, or why deep learning in general is interesting to accelerate. So I will just give you one example, which was still done some time ago, but I think the conclusion is still valid today, is that so, you know, if we try to train neural networks on these big data sets, for example, ImageNet 22K with ResNet 101, we did the measurement at IBM, and you know, the conclusion was that essentially, you know, these numbers of kilowatt hours, they essentially correspond to 2 hours of home 2 weeks of home energy consumption. So this is quite significant. So, and this is just, you know, training one model one time, right? But you never just train one model one time, you train it multiple times, you sweep, you know, the learning rate and all kinds of different parameters. So, you know, thinking that each of these instances, they consume 2 weeks of home energy consumption is quite significant. So, and, you know, of course, it's also time consuming. And, you know, in case of inference, it's definitely the power consumption that is coming from that is resulting from, you know, these multiple GPUs is prohibitive for applicability in like Internet of Things or edge computing, right? So yeah, now this is where this computational memory comes into play, right? So now how can we do inference with this kind of in-memory computing chips? Right? So the idea is, so you have like a deep neural network here that is shown. So the you know, here these are the synapses, the neurons are the dots, and then so each synapse will be mapped to a certain cross point in this architecture, which represent the synaptic weights. So each synaptic weights will be programmed on certain devices here that are arranged in a crossbar, and then to perform the forward propagation, we will essentially apply the input activations on the rows and get you know, the column outputs. And that will give us the output activations that we then have to propagate to the next layer, which would be essentially on another crossbar or another array in the system, right? And then we do this until we essentially arrive at the end of the network, and then the final result will be given by the output here. So you know, for example, in this case, we have this input image, and then, you know, we will just look at which of these neurons is the strongest, and then that will give us the results. So in this case would be a 2, for example. So the idea is, yeah, so again, we train the neural network first, typically on externally, right? So in this case, you can do training on chip, but I will not cover that in this talk. So typically what we do is we train the network externally using conventional, you know, software, GPUs, etc. And then we take the trained synaptic weights, we map them on an array of those computational memory cores, and then each of these cores will perform matrix multiplications that correspond to each layer of the network. So that's the idea. So, and why PCM can be useful for this? Okay, I heard something. Anyway. So why can PCM be useful for this? So there are the main property of PCM that we use for deep learning inference is this fact that we can, it has a kind of an analog storage capability. So it cannot just store one bit, but it can store a range of different resistance values that can be obtained by changing the current that we send in order to program the device. So this is what is shown here. So, you know, we start with the lower current, so we are here in the crystalline state, and then as we increase the current, we essentially started change, you know, the size of this amorphous region, and as we change the size, then the resistance increases kind of gradually. So it's not like just a 0 and 1, but you can reach all those different intermediate states. So that means you can essentially store, you know, an analog weight value inside this phase change memory, and you don't have to just use it in a binary fashion. So this is interesting because that allows us to essentially, and actually this is what we do in practice, we can just store a synaptic weight in one device, right? Just by using, you know, this range of different resistance values that we can obtain. And this is interesting because that really increases the density at which we can store the weights, right? So, but the drawback though, and this is what we have to deal with when we build, you know, these multi-core chips, are the non-ALTs of phase change memory, and there are a few here that are illustrated in this chart. So when we measure these resistance states over time, as you can see, they are not stable, right? So essentially, the resistance tends to increase over time, and it's also very noisy, especially in the states in the middle, which are those kind of intermediate states where the amorphous region is not very well defined. It's like there's a lot of percolation paths in there, and everything that leads to high noise. And also, we see in general the resistance tends to increase over time, and this is a well-known property of phase change memory, which is called resistance drift. And this will never stop, essentially. It will keep increasing like this for like 10 years. But it's a log scale. So that is the good thing about this, is that at some point you kind of barely notice it, because it has been drifting for so much time that, in order to notice a significant increase in resistance, you need to wait for an order of magnitude in time, right? But in general, we have to deal with these kind of issues when we build those chips. So now I will go to the presentation of the latest chip that we have built, so which is called this IBM Hermes project chip. So here, this is like a micrograph of the chip, where you can see, so it has 64 PCM cores. So the core is basically what you see here, right? So I applied it here in this red box. So each of these are PCM cores, and in the middle of the chip, we have a global digital processing unit that we use to do like LSTM activations. Here, this is a picture of the setup that we use to characterize this chip in the lab. So the chip is basically sitting under this, in the socket here under the heatsink. And then here we have an FPGA, and this PCB board is essentially just a bunch of power supplies. What the chip has, it has 64 256 by 256 cores based on phase change memory. So these are the matrix vector multiplication cores. Each core has local digital processing units that can be used to perform some affine scaling operations and also ReLU activations. So this global processing unit in the middle can implement the LSTM activation function, so that is sigma and tanh, and also all the cell state computation that is required as well. And also we have on-chip digital commutation link that allow to transmit data from one core to another core, and also to the GDP. So this chip is pretty big, actually. It's 144 millimeters square. Each core has approximately 1.4 millimeter square size. So now to describe, so each PCM core is essentially looking like this. So again, we have a 256 by 256 array of PCM unit cells. So this looks like just the crossbar that I've shown before. So the main thing, though, is that each unit cell is not just a single PCM, but actually 4 PCM arranged in a differential configuration. So that is to support negative weights. And then why we have like 2 PCM devices per SEM is just for redundancy. And actually, I will show that when we program the weight on 2 devices instead of 1, we can actually increase the accuracy. So that is why we have 2 devices instead of 4 devices per unit cell. So there are 256 ADCs. So actually, each column of this crossbar has a dedicated ADC, and that is to increase the throughput as much as possible. So we actually have 1 ADC per column here, and also a local digital processing unit that is this here to do again these fine scaling operations and ReLU. We have also parallel device programming capability with on-chip DACs. So we have 32 DACs on each core, so that is we can program 32 PCM devices in parallel. And these are the numbers that we measured for the matrix multiplication efficiency here. So 10 teraops per watt, and about this number for the throughput. So what we can do with this chip. So first thing, it can have a maximum of 4 million weights. So we can also do, using these on-chip links. Basically, we can do data aggregation in the LDPU to support layers larger than 256 by 256. So most of the layers that we encounter in neural networks, they are actually bigger than that. So we need multiple cores to implement them. And then, usually if the layer, has more rows than 256, then we need to combine the results of 2 different cores. So this we can do by sending the data from one core to another core, and then doing the sum at the output in the digital processing unit. So this is supported, and this is what we actually do in all the demonstrations that I will show later. So the chip can support CNNs. So, you know, as I said, we have ReLU, and we can batch norm, we can do this in the LDPU. So activations are represented in 8, and we have FP16 format for those batch norms. So basically the LDPU works with FP16 arithmetic here. And then also we can support LSTMs. So not like any LSTM, but essentially, you know, an STM where you can fit one cell on the top half, because this guy doesn't communicate with the bottom. It communicates only with the top, as I've shown here. So essentially, you have to basically put the LSTM cell here, or basically it doesn't have to fill the, you know, use all the cores, but still you have to put the STM here, and then, you know, connect the output of the LSTM cell to the GDPU so that you can do the activations and the cell state computation. Yeah, so what we can do with the bottom in this case is to put like the fully connected layer. Right. Okay. So now first, I mean, the first thing we do when we want to implement a neural network on this chip is we need to program the synaptic weights, right? So how do we program the synaptic weights? Is by what we call iterative programming. So essentially, we map the synaptic weight to some conductance value, that is this G target. Then we will send a certain pulse to this device with certain current value. Then we will read the conductance, and then, you know, compute the difference between this conductance and the target, and then change the amplitude of the pulse until the difference is small enough. So this is typically what we do, and this we do like at the individual device level. And that is simply because there is no way you can just send the same pulse to all the devices and hope to reach the same conductance. It doesn't happen because with these large arrays, there's a lot of variability. So you will never reach the same conductance when you send just the same pulse. But with this technique, you can program pretty accurately any conductance value, and then you just do it, you know, for every device, and then that allows to essentially get the states that you want, but with some variability. So as you can see here, these are measurements from the chip. So you never get like exactly the correct value, but you get like some kind of distribution. And here, right away, it's just 16 states, but I can put any number. I could put 100 states or more. I mean, it doesn't matter. But each state basically has this kind of standard deviation, right? And this is the important thing. So there's essentially a distribution of conductance values for that essentially depends on what you program in the array, right? So for conductance of 0 to 10 microsiemens, you can see that essentially the standard deviation increases, right? So that's typical. But yeah, we are not tied to these 16 states. I mean, it can be any number of states, but you know, each state will have certain standard deviation that it has shown, right? So, and now once we have programmed the weights, we can do matrix multiplications. So I will explain how we do this in analog. I think it was also covered in the morning by Onur, but just to recap what we do. So we have a matrix here. We map it to conductance values. So that is basically the A11 corresponds to G11, A12 to G12, etc., like this. And then we will map the X, so which is the input vector, to voltage values. So this V1 and V2 here. And then the result of the matrix multiplication we deciphered from the current. So that is basically using Ohm's law to do the multiplication and Kirchhoff's law to do the additions here. And the nice thing about this is that potentially this is done really at the place where the data resides, and also it can be done with O1 time complexity, given that we can apply all the inputs in parallel and read all the currents in parallel, which is the case in the chip, because as I said, we have 256 ADCs, so we can read everything in parallel. But yeah, because of you know, the conductance distributions that we have and the drift and all the stuff that I've been talking about before, you don't get floating point precision with this, right? So here, this is again a measurement from the chip, and as you can see, so it kind of, you know, there is a spread around the red line, which would be like a floating point calculation, right? So this is expected, and now let's see how it looks on all the 64 cores of the chip. So here, this is just the biggest histogram that essentially, comprises all the 64 cores and shows, the MVM, the matrix multiplication error after programming. And here, so we did it for one device programming. So basically where you map the weight onto only a single device, and 2 devices where we use, the full 4 PCM cell. And then, so as you can see, we can reduce the programming error when we use 2 devices, and that is because the noise just averages out, right? It's very simple effect of, that the noise just averages out between the 2, and then so we get these reductions. So instead of here, this is in 8 units, so the standard deviation reduces from 4.5 to 3 in this case. And we could see that, so when we compute the weight error now from these results, what we can see is that indeed, this increase in accuracy comes from a reduction in the weight error between 1 device and 2 devices. And that is essentially coming from just averaging out the random errors, programming errors or drift or whatever. So everything gets averaged out. Yeah. And then if we measure this over time, so as it's not a surprise that the error also increases because of this resistance drift effect that I've shown in the previous slides. So here, and so if we want to compare this with kind of digital computing, we kind of computed what is this error when we essentially have 8-bit input, output, and n-bit weights in just the conventional digital implementation. And then, so what you can see here is that this, 2-device programming resides essentially between 3-bit and 4-bit. So one thing though that I want to point out here is that this is only valid for the very specific distributions that I've used in this experiment, which is like uniform input and uniform weights. If you change the distributions, these will change. Both the digital and the PCM, the errors will change. And the reason is, that so I could just, so if you have a uniform, then everything spans the whole weight range, right? Equally. So digital is actually quite good at this because also the quantization noise is uniform, so it gets pretty good performance. And actually, this device might look quite bad. I mean, thinking that this is worse than 4-bit. But on the other hand, if I would take a Gaussian that is essentially, has most of the values here around 0, then this will be better because the noise is much lower when we are close to 0, although the digital will have a lot of quantization. So I just want to point out that, this is not like, it's good. It's always good to do these comparisons, but like if you want a complete picture, you should do them for all possible distributions, not just like here. So this one, just what I want to say. So, but given all this, of course, it's not expected that you can just take a network that was trained with the GPU, without any tricks, and then map it on the chip and hope that it works. This is obviously not the case because the chip doesn't do accurate computations. So what we have to do is, and this is the same for any reduced precision digital network, is that we have to do some kind of custom training for this. And so how we do the custom training here, unlike reduced precision digital, is that we will essentially we'll inject noise on the synaptic waves during the forward pass in order to, and this noise is essentially, we'll try to have the magnitude of this noise comparable to the, the width of the distributions that I've shown previously. And by doing this, so because then you will make the network more robust to this noise because it will have seen it during training. And hopefully you can hope that, when we will use the same noise during inference, then we will not suffer a lot from a big accuracy drop, right? So now let's see how it looks when we do the actual experiments on the hardware. So the first network we looked at was a ResNet 9 for Cypher 10, so which has almost 2 million weights. It's a custom version of it. So yeah, and essentially basically what the chip does is all the computational layers operations that are done with this analog and digital computation. So basically the matrix multiplications are done in analog, batch norm and ReLU are done in digital, and that is all done on the chip. And this is how the network looks like when we map it on the chip. So essentially the first layer goes to the first core, second layer needs 2 cores, so we put them on 2 here. Third layer would be here, so it needs 4 cores, etc. And then all the last 3 deep layers, they need essentially the whole row of cores that need to be implemented. And again, as I said, so you know, in order to accumulate the results from the different cores here, we use the on-chip communication links, and then we do the additions inside the LDP. So basically, we don't have to take the data out when we have these big layers. Everything is done on-chip. So what we got is this kind of accuracy. So the software baseline was 93.67. On-chip is 92.81, which is less than 1%. So it's not as good as the software accuracy, but still pretty good given that, you know, yeah, so the error is basically less than 1%, which is acceptable, I think. And here we have the breakdown. So this is kind of, you know, simulations to understand where the error is actually coming from. And what we can see here is that essentially, so both the quantization and the weight noise decrease the accuracy as expected. And so most of the accuracy drop is actually coming from the PCM devices, which is good because then it means that essentially there's no big issue with the chip in terms of nonlinearity or any other thing that could happen in the peripheral circuits. Essentially, as soon as we can improve the noise of the PCM devices, we will get better accuracy. So this is actually nice. Yeah, so now a second network that we looked at is essentially something that could you know, use fully the chip, so all the 64 cores. So this is an STM that was used to generate image captions. So here there's a couple of things that are not actually done on chip because the chip doesn't support these big embedding layers, so we have to put them outside. But essentially, the whole LSTM plus the fully connected layers are fully on chip, and it's also using the GDPU to do the activations and so on. And so here, so we characterize the accuracy by this blue score, which is essentially, you know, it is basically matching the different n-grams that are produced by the network and compares them with the reference caption. So basically, the higher the better in this case. And then, so as you can see, I mean, we get essentially the same results as the software. And there's actually a live demo running in the lab. If you come to Zurich anytime, I can show it to you. This has been programmed, I think, 6 months ago. It still works perfectly. So that shows that this drift is actually not that bad, at least for these kind of networks. I mean, these STMs are usually very robust to these nonlinearities. Yeah. So now let's come to the performance, of course. So I talked a lot about accuracy, but performance is also important to consider. So that table is very busy. So I will just highlight the main things that we found when we looked at, you know, comparing with the different chips that are out there, both resistive memory and also the SRAM SIM chips. So if you look at this line here, we have the highest cipher-10 accuracy, so that is good. Also, if we compare the throughput per area among the resistive memory chips, at least, so I don't know about the ISSCC 2023, probably there's one that beats us there, but so if not, then at least the previous ones, we are essentially 15 times higher. We still don't beat the SRAM, but among the resistive memory chip, the throughput is significantly higher. On the other hand, you cannot just get everything right. So there's always one thing that will suffer from this, and in our case, it's essentially the TOPS per watt, which are a little bit lower, and that is because of this very large amount of ADCs and LDPs. So what we could see, I mean, I measure the power, and essentially most of the power, 75% of the power is ADCs and local digital processing units. So that's definitely something that we have to improve in the future, especially the ADCs, which account essentially for 50% of it. Yeah, to make them more energy efficient and try to improve these numbers a little bit. Although I have to say that the improvement in throughput is kind of outweighing the loss in TOPS per watt that we have compared with the other chips. So I would say the trade-off is still acceptable in this case. So now to finalize the talk, so I just wanted to talk about something that we've been doing recently, which is essentially to open source the whole simulation code that we use in order to evaluate the performance of networks that we map on computational memories. And this is called this IBM Analog AI Hardware Acceleration Kit. It's a very long name. You can access it in this on this URL. It's fully open source. So so there is a GitHub essentially that that can simulate essentially the whole operation of an analog neural network. So that includes the forward, the backward pass, and the update. So this can be used for both inference and training. So it has a lot of different functional models of different materials with adjustable parameters. So we have both training and inference models. So for training, we have, and everything is calibrated on hardware. So we have ReRAM models, we have ECRAM, we have capacitors, a bunch of different devices that can be used for training, and also this, a fully calibrated statistical model of PCM with drift and programming noise model, etc., that are basically calibrated on the hardware. And so GPU is fully supported, and also there's quite a bit of online documentation on this kit. Yeah, so if you are interested in learning more about this field, or just trying out, what accuracies we can get on different networks, using models that are calibrated on hardware, it's a very useful toolkit, I think. And for those who are not keen on, using, are not very proficient in PyTorch, or that just don't want to code, there's also a web interface where you can just do basically what I shown in the previous slide. So you can build your network, using just blocks like that. So just add layers basically compose your neural network, and then select the presets, so the noise model, the device model that you want to use. Like you can select between SRAM, ECRAM, and everything you like here. And also you try out different optimizers to kind of see what changes in the accuracy when you change that. And then you can also, when we do inference, for example, you can also visualize like the variations in the weights, for example, that happen with the statistical PCM models. Here you see, for example, the drift so what it does on the weight, for example, etc. So I think that the most exciting thing about this is not yet there, but we are trying to hook up this interface to a real hardware chip in the lab in Zurich. So this is going to be done hopefully this year, I hope. And I think this will be really interesting, because then, basically the users will be able to implement their own network and then actually run them on the hardware. So so to conclude, so I've talked about computational memory based on resistive memory devices, and that they could play a role in developing energy efficient processors for deep learning inference. And essentially the main thing here is that we don't have to shuttle around the synaptic ways. They are, physically stored in the memory devices. We don't move them around, and we do the multiplications directly at the location of the data. So I've presented this IBM Hermes project chip that could establish near software equivalent accuracy with PCM on several AI tasks. So we also, went beyond most of the other demonstrations that were just at the macro level, but actually demonstrated the integration of analog and memory computing with some of the essential digital compute blocks. So like this, affine scale blocks, and activation blocks also, and also the on-chip communication fabric. And then, of course, this is still, far from the systems based on DRAM that have been presented previously in this tutorial, but still with some innovation both at the device, circuit, system, and software level. We still think that these PCM should be promising to build like a full-fledged accelerator based on non-environment computing. So thank you. Yeah, of course, I would like to acknowledge all the contributors of this work, which is essentially the in-memory computing group at IBM. And we have also a lot of collaboration within IBM and also outside of IBM with different universities. So thank you very much. If there are any questions.
I'm just wondering if the resistant material will start to degrade if you program it multiple times?
Yes, yes. Of course, finite endurance is there. I mean, so it's not like DRAM. So yeah. So first of all, so in these applications, we don't really program it a lot because you just have to program every time you get a new network. So the whole idea is that you can just have your whole network stored fully on chip. Unlike the SRAM chips where they need like a weight buffer and then, you know, they just operate 1 or 2 layers at a time and then, you know, they like send data from the weight buffer to the chip. So here the whole idea is to just really have the whole network stored on chip. So you just have to program once and then, you know, the network will run. But on the other hand, yeah, so the endurance of PCM is essentially, you know, typically like 10 to the 9 cycles. So that is better than flash, but of course worse than DRAM, which is essentially unlimited endurance. So yeah, there will be some endurance issues at some point, but if you just use it for these kind of like inference applications, then they should not be like too detrimental actually, because you know, then, I mean, you will see a degradation when you program 1 giga networks. So yeah, it might take quite some time.
Using it in a real environment.
Right.
Might have missed if you talked about it, like train your network and then.
Correct. Then you just offload it and then you do a bunch of inference, and the read endurance is unlimited. Okay. The read endurance is unlimited. It's just the programming that, you know, will create issues eventually. Yeah. Yeah.
My name is Tracy. I'm from University.
Sure.
So the drifting, the resistance that you showed,
yeah.
To be deterministic.
Yeah, that's why we can compensate for it exactly. So I mean, yeah. So I've not really talked about how we compensate for drift, but in all these implementations. So yeah, exactly. So what we do to compensate for drift is very simple. We just apply a constant scaling factor at the output. So that's how we can. So we can at least compensate for that. Let me just get. So yeah, we can compensate for the average increase. We can compensate for it by just applying a constant scaling factor that would have to be recalibrated every like X, minutes or hours or every day, let's say, right? So we just recompute the scaling factor every day, by just measuring a subset of devices, for example, in the crossbar, and then we can have, an average compensation for that. What we cannot compensate for is the fact that these slopes are different. So you see the slope, for the low devices is lower than for this one. So that is expected, and this is what we cannot compensate for. So essentially, what you see is that the weights will start kind of to diverge, and that is, these random, this random divergence of the weight, we cannot compensate for them, but what we can compensate for is just this average shift in conductance. So that is not a problem.
So you're talking about the PCM level for people in inference. What about the training?
Yeah, exactly. So I usually have both training and inference covered in this talk, but like I thought it would be too long, so I just put the inference. So yeah, we can also do training. I mean, the only thing though is that training requires a lot more things that you cannot do in those arrays, right? So especially with respect to the weight update. I mean, so the weight update, you cannot do it accurately with these devices because there's a lot of nonlinearity and stochasticity, etc., and the weight updates. So typically, I mean, the way that we could manage to do training with this is essentially to have like a digital accumulation of the gradients, and then once they reach a threshold, then you send like some blind pulses to device to increase the weights. And since the gradients are essentially accumulated and computed in digital, then backprop will take care of any error that happens when we update the weights here, and then everything will work fine. But having it like a fully analog kind of training, I know there are some papers that are claiming that, but I personally don't believe that this is reliable. I mean, you can probably do MNIST with this, but if you want to train ImageNet or something, I mean, good luck with fully analog. I don't think it's going to work. Yeah. Sure.
I'm from University, and my question is that when I hear your explanation, is that PCM has the same version of the organization that
Correct, like ReRAM.
Yeah. And so my question is, what are the specific advantages and disadvantages of this RAM over the other emerging devices?
Yeah. So essentially the main advantage is this one, the analog storage. So I don't think this is as reliable in ReRAM as far as I know, because it's pretty hard, I think, to program all these intermediate states in ReRAM, because you have to, I mean, we have this filamentary kind of conduction mechanism, right, where you essentially, it's very hard to control the width of that filament. And so, you know, you can do multi-level programming, but in my opinion, it's much more difficult with ReRAM than with PCM. Where we essentially are modulating a volume here. So this is much easier to achieve, and reliable multi-level storage is much better, I think, with PCM. So that is one of the strengths of this PCM devices, I think, is the fact that this multi-level storage can be achieved very reliably. The drawback is here, so it's the drift. The drift is not as present, I think, in ReRAM or other devices. And the noise also is not small in PCM. Another thing that is not great about PCM is the fact that it still required fairly, I mean, not crazy high voltages, but still, you know, it needs something like 2 volts in order to reach the threshold voltage at which you can pass, enough current to program it. So that is something that essentially that is a bit of a problem when we want to increase the density, because I mean, these kind of accelerators will essentially be only very competitive with respect to digital if we can store like billions of weights on these chips, right? I mean, that's the hope that you can do this, because otherwise I think the digital will always beat it or just be very similar to it. So the idea is really to have like a very high density of weights on a single chip. When we can achieve that, then I think this kind of technology can be extremely competitive. And yeah, one thing that hinders this is, again, the fact that, you know, they require both relatively, I mean, not small voltages, at least that are not, you know, these, like, let's say 2 volts or so. It's not, you cannot, you know, have just a single transistor to support that. So you need usually more, and also they need the, you know, these the programming current is not that small, so it's like on the order of 100 microamps or so. So you also need to have enough, you know, transistors to drive this current. So that is maybe, yeah, the main drawbacks, I would say, maybe compared to ReRAM devices. Yeah, exactly. So all these, I mean, drift also is present in ReRAM, but I think it's less probably than here. Although, as I said, drift is not the biggest issue here. So, I mean, the high voltage is, I mean, definitely ReRAM is worse than PCM for that. I mean, it needs also, and also it still need, I mean, as most of the works I've seen, they still use this forming process where you need to apply very high voltage at first on the ReRAM to make it operatable. So here we don't need this with PCM. And so, yeah, I would say the voltages are similar, or it's probably higher in ReRAM. I think you probably need to support like 3 volts or so to have reliable operation with ReRAM. Although I think the programming currents, at least from what I've seen, they are lower. So this is one good thing about ReRAM, that you can usually program it with less current than PCM. This device, yeah, this device is not large, so that is 100 nanometer here. Yeah. So the device, the PCM device is very small, but you know, what takes most of the area of the unit cell is not this one, but it's the transistors and the wires, because the wires are actually, I think, even bigger than the PCM devices. So yeah. Yeah. Yeah.
How you define your mapping strategy? Say what layer that to what kind of force and
Yeah, that's a good question. I mean, here we did everything by hand because this is just like one chip, but now we're in the process of building a full software stack that essentially does this. So it will do the mapping optimally and kind of, you know, optimize with respect to communication. So essentially the idea is, since it's a lot easier to communicate within one row, than you want your layer to fit usually, I mean, within one row. You don't want to lay like a vertical, you know, kind of layer, this is less easy to operate. So that's why also you see here that the CNN, essentially each layer is spanning like either one full row, but it's always like within one row, you know. So yeah, I mean, this is ongoing work. I mean, right now here it was just done manually, yeah, because we know how the chip operates. But, yeah.